Welcome to this technical guide on mastering the challenge of resistors in pulse load applications. We will explore how to analyze pulse conditions, select appropriate components, and ensure robust circuit performance. A pulse load can generate intense heat, causing the resistor's temperature to increase rapidly. This overheating can lead to damage, a change in resistance, or complete device failure. The threat is defined by pulse duration, shape, and frequency. Short pulses localize heat, while long pulses cause a greater temperature rise. Pulse shape determines if peak power or total energy is the limiting factor. Repetitive pulses require considering the average power. The first step is to systematically define your pulse condition. Determine the peak power, duration, and period to compare against the component's specified capability using this flowchart. Understanding the pulse load diagram is key to component selection. These diagrams specify the maximum permissible peak pulse power for a given duration. Find your pulse duration on the x-axis and move up to the curve for your component size to find the maximum peak power. When reviewing pulse load specifications, ensure the diagram covers the full resistance range and explicitly states the permissible resistance change, or delta R, to ensure a safe and reliable specification. Comparing film resistor technologies shows that pulse load capability is influenced by the resistive film material, trimming pattern, and available resistive area. Thin film MELFs offer the highest capability due to their large area and homogeneous heat distribution. The carbon film MELF resistor is the SMD champion in pulse load capability. Its large resistive film area, helical trimming, and stable carbon film material provide superior performance compared to equivalent case-size chip resistors. You can improve the limited pulse capability of thick film resistors. Solutions include double-sided printing for heat distribution and omitting the trim cut to avoid hotspots and use the entire resistive area. For massive pulse energy, wire-wound resistors are ideal. Their large metal wire mass and ceramic core allow them to dissipate extremely high pulse energy for short durations. A vitreous enamel coating further improves pulse load capability. Wire-wound resistors offer exceptional overload capability. A typical Vichy wire-wound resistor can handle about 1,000 times its rated power for a 3 millisecond pulse, showcasing robust performance against short-duration transients. For short-duration transients in current sensing, element mass is key. Power metal strip resistors have a thick, self-supporting resistive element, resulting in a much larger element mass compared to thin film technologies, which boosts pulse performance. Your toolkit for mastering pulse load design includes analyzing the threat, scrutinizing the data, and selecting the right technology. Remember to use the further resources provided, including the Joule Wizard calculator, for specific application questions.